Okay, welcome back, Physics 30s, to our next lesson. This is part 2 of the Compton's effect. Okay, so in the last lesson, we focused on understanding the concept of what the Compton's effect is. And this was the idea that light is going to act like a particle with momentum when it crashes into an electron. It doesn't have any mass, but because it has energy, it's going to have momentum based off Einstein's equation. And we talked about when it hits that electron, it's going to give up some energy and then bounce off with a different frequency and wavelength. This is going to be an elastic collision where energy is conserved, and we can calculate the energy of the photon with HF, the energy of the electron with half mv squared, and the new photon with HF prime being the new frequency. We can also track momentum, as momentum will be conserved, and we can find the momentum of the photon with HF over c, momentum of the electron with mv, and momentum of the new photon with hf prime over c. So now that we know how this effect works, today we're going to do the full calculations of the Compton's effect. This is what our questions are commonly going to look like. But our first step in solving these is trying to figure out what that resulting photon is going to look like and see how the wavelength is going to change. And for that, we're going to use this equation. This equation says that the change in wavelength of our photon is related to the angle that the photon is going to bounce off at. There's a lot of other stuff here, but this is h, Planck's constant, c, the speed of light, and m, mass of an electron. You don't need to know how to get to this equation. However, when we look at it, we notice that all of those are constants. So if all of these terms stay the same, and 1 is going to stay the same, and cos is just an operation, this gives us a relationship between the angle that the photon bounces at and the change in wavelength. Now, I do really want to emphasize that that is change in wavelength. This doesn't tell us the resulting wavelength of the photon. It says how much it changed from the initial photon. So that's important to remember. And in the questions we're looking at, the photon is going to make this path because it's knocking an electron off in this direction. Since the electron is stationary, the photon is going to give energy to this electron. So that means that this photon has to be less energy than this one. Now I want to make sure we fully understand the characteristics of a lower energy photon. Lower energy means less frequency. And from the universal wave equation, that also means a longer wavelength. I think it's easy to think that we'll have a shorter wavelength and this change will be getting smaller. However, with the energy to get smaller, our wavelength actually has to get bigger. So when we calculate this change in wavelength, we need to add that to the initial wavelength in the question we're going to be solving today. And just before we get into the new calculation, I want to note that the angle is measured from where the photon would have traveled if it did not undergo a collision. So that's measuring the angle right here. It's often going to be less than 90, but this angle could actually be anywhere in the range of 0 to 180 degrees, and we'll still solve it in our same way. Okay, so now with that new formula, we're ready to try these questions. It's going to be a fair amount of calculating, but we'll go through it in each step. The example we're going to look at says that an X-ray photon with a frequency of 6.0 times 10 to the 18 hertz collides with an electron and scatters at 30 degrees. That's the X-ray photon. Determine the velocity of the electron. Okay, so as I said before, first thing we need to determine is what that photon is going to look like after it's bounced off the electron. So we start with this formula. Change in wavelength is equal to h over mc times 1 minus cos theta. It told us the angle in the question is 30 degrees, so we plug in that 30 degrees along with all these other constants, and we get a number of 3.25 times 10 to the negative 13 meters. Now I'm going to emphasize once again, that is not the new wavelength, that is the change in wavelength, so we need to apply that to our initial wavelength. Now it didn't tell us the initial wavelength, but we do have the frequency, so we can determine it from the universal wave equation. Rearrange for wavelength, and I get the answer to be 5.0 times 10 to the negative 11 meters for our initial wavelength. So now I have my initial and the change. Should I add or subtract them? That's where we need to know that, well, this is bouncing into a stationary electron and giving away its energy. Then the resulting photon must be less energy than the first one. So should I add or subtract? This is where we have to remember that higher energy is higher frequency and lower wavelength. So lower energy photons are lower frequency and longer wavelength. So we need to add this change. So I take my original wavelength and I add this value that is the change, and I get a value over here of 5.0325 times 10 to the negative 11 meters. Okay, so that's the first step, and now I have my initial wavelength and my final wavelength of the photon. And now I'm able to solve for what's going on with the electron. And the first way I'm going to solve this is with momentum. So first I need to determine the momentum of this photon. And we have the formula P is equal to HF over C. And that works really well for using frequency like I initially had, but we've kind of converted everything into wavelength here. So if I take the universal wave equation, I see that C over F is equal to wavelength, and so F over C is equal to 1 over wavelength. So I'm just going to take this F over C, which I see right here, and put in 1 over wavelength to get this new formula. So I'll be using P is equal to H over wavelength for calculating momentum. So let's find our starting momentum of the initial photon. I take my Planck's constant in the form of joule seconds, divide by my wavelength, and I'm getting a number of 1.326 times 10 to the negative 23. Use the same formula for our resulting photon, and I get the answer of 1.317 times 10 to the negative 23. Okay, so we have our momentum of the initial and final photon. Now to determine the momentum of the electron, we need to look at x and y separately. So we need to break up this momentum into its x and y components like this. We knew the angle here was 30 degrees, so this shouldn't be too hard. We'll just use sine for determining this side and cos for determining this side. And when I take sine 30 of this momentum, I get 6.587 times 10 to the negative 24. And when I take cos, I get 1.41 times 10 to the negative 23. Now let's look at the x and y components of that electron. I think the easiest place to start is with y. We initially had no momentum in the y direction here. We had momentum of 0 in the y. So that means over on this side, if I have this momentum in the downwards direction, let's call that negative, I should have the same value in the positive direction. So I can put that same number right there with a positive and negative. That equals out to the same 0 that we had at the start. Now looking in the x direction, my initial momentum was entirely in the x direction. So if I started with this amount, I need to finish with the same amount. Now I know that I have this already in the momentum of the photon. So if I take this value, subtract this value, I should get the remaining amount of momentum in the electron. I complete that, and I get a number of 1.851 times 10 to the negative 24. Now all we have to do is use Pythagorean theorem, a squared plus b squared is equal to c squared, and our momentum along that line is 6.842 times 10 to the negative 24. Okay, so I know that's a lot of work, and we're not quite at the answer. We just have one more step to go. That was the momentum of the electron. Now we know that equals mv, and we just need to divide by mass. So I've simplified things a bit here. We have now that momentum of the electron is equal to mv. Now we just need to divide by the mass of an electron, which is 9.11 times 10 to the negative 31, and we get our answer of 7.5 times 10 to the 6 meters per second as our velocity. So that's how you calculate it with momentum. I know it's a lot of equations, but hopefully some of these are familiar from Unit A. If you need a refresher on that, you can go back to those videos. Now there is another way to solve it because this is an elastic collision. We could also use energy, which if we've already done the step of determining what the photon is going to look like after the collision, I think it's a little bit easier because we don't have to use angles. So now let's do the calculation with energy. So I'm going to start at this point when we've already determined the wavelength of the photon after the collision. Now, my energy equations is usually E is equal to HF is the energy of a photon. So since that equation is simplest based on frequency, I'm going to use that frequency that we have in the question. So I'm going to convert this back to 6.0 times 10 to the negative 18 hertz. Now I also need to turn this into frequency. I'm just going to use the universal wave equation there rearranged. C over lambda should give me frequency, and that gives me a number of 5.961 times 10 to the 18 hertz. Okay, so now that we're in hertz, let's turn this into joules, figure out the energy we have. The energy at the start, again, that frequency times by Planck's constant, so just times by h here in our equation, gives me 3.978 times 10 to the negative 15 joules. Now let's figure out the energy at the end. Again, all we have to do is multiply by h since we have the frequency, and I get 3.9523 times 10 to the negative 15. Now in conservation of energy, we don't have to worry about directions because energy is a scalar. So it's nice here that we just look at starting and final energy and don't have to break up into components. So that means if I take my initial energy here and subtract my final energy, I should get the energy that is in the electron. So I subtract those and I get 2.569 times 10 to the negative 17 joules. Now all I have to do is determine the velocity from that, and for the energy of an electron is equal to half mv squared. I'll times by 2, divide by mass, and square root, as you can see in the equation here, and I get the same number of 7.5 times 10 to the 6 meters per second as the velocity. Same answer as we saw before. Okay, so I know those are long examples, but I hope that video helped to explain how to solve these types of questions. Thank you so much for watching the video, and I will see you in the next one.